Okay, so we're going to implement a binary search tree. I am going to use your guys' help so we can like code it together, walk along the like step by step and see what we want. So a binary search tree generally is a tree that has one node, or each node in that tree has at most 2 children nodes. So this node usually has a left and a right node, and then a value inside of it. So maybe we can start by defining the node that is specific to these trees. So what am I going to put in here?
Would you put your left and right values?
Mhm.
Which way the node is going? Awesome.
I guess we can start it off with none. For here, when we're initializing a node, we'll probably send in a value. Okay, so left is none, right is going to be none in the beginning. And then what else do we want?
Like the root or the value?
The value, yes. Value equals the value that we send in. Okay, so this will create a node for our tree. So now let's create a class BST. And this binary search tree is just going to have a root, which is empty at the moment. So one way of doing this, we can say our tree equals BST. And then we can say, well, we would need an insert function. So actually, let's not put a BST class. Let's just create nodes. I think you guys were doing this with Adam yesterday, with the linked lists. So tree, we can start off with a node, and then we can send in whatever value we want. Let's say 50. So currently our tree is just going to hold a value of 50. I don't know why I was printing that out. So tree.value, we should be able to print out the value of the beginning. Okay. So what types of functions would we need to for our tree?
Add node.
Yeah.
Okay. An add, or a lot of times it's called an insert. So we can insert a node onto the tree. So what we would want to send in, what would we want to send in actually to our insert function?
A new value.
A new value, okay. And what else?
What it's pointing to.
Yeah, so do you mean like the tree? Like the tree itself? Or the root of the tree?
Class node, is that, are we just in the node or are we just in the tree?
So we're out here. We're not in a tree class. We can actually, yeah, we'll just create a class tree. or BST. And then,
For the node class, I noticed that our templates typically have the node class at the bottom. Is having it at the top this standard practice typically?
so if you're gonna use the node class in here, like if I'm gonna use node inside the BST, it has to be defined before. Yeah. I cannot type today, guys. Okay. All right, so if we say we have this, and then I can put this function inside of our BST class. So whenever we want to insert to our tree, we would just have to say tree.insert and then send in a value. Okay, it's going to pass here. This won't work anymore because tree is now a class instance, and if we said tree.root dot so it's not here, we would have to put in init function, but this is okay. Okay, so how are we going to insert? Can someone just on a high level tell me what are the use cases? What are some use cases? So
we're going to insert at the root. We're going to insert at the end of the tree.
okay, so insert at root. So what does, if we're inserting at the root, what does this mean?
So if the root is none, that means we're replacing it with the first value.
Yeah. Equals none. So this is one. So we're either inserting at the root or we're not. So in the case of not, what do we have to think about?
You have to basically traverse the tree and then identify where it would fit in the tree.
And what are the rules for a binary search tree?
So you would compare the left and right values.
Okay, and what is happening with the left and right? So if
Left is lower and right is higher.
okay, so if our val is smaller than root or smaller than wherever we are, then we have to go left. Else we are gonna go right. Okay, I think this is a good starting point. So let's check for if root equals none. So if root is none, so this root is here, that means we would have to access it. Let's just say self, sorry. So self
Do you gotta initialize that BST class?
dot root. We can initialize it down here like this. Oh, you mean like to put an initializer? Yeah. If I don't put an initializer, what does this become here? So if I left exactly class variable versus an instance variable. So this root would be attached to the class, and it can change if we have multiple instances. So if we want to make sure that we have different trees having different values and stuff like that, we would have to put this inside an initializer and make it a instance variable. Okay, so now we're saying self.root is none when we initialize it. So when we want to insert a new value, if we're still at an empty tree, then what do we do?
self.root becomes the node.
Self.root equals a new node that we create with our our new value. And then we can return root or self.root. Yeah, I think usually when you're creating a new one, you can return the root, or you can return a new node. For insert, actually, let's say we're not going to return anything. We're just going to return. This should work. And then let's test it out. So tree.insert 3. Oops. 3, and then print tree dot root dot values. And our value is 3. Okay, so we were able to create one node at the top of the list, or at the top of the tree. So now what if we want to do an insert again? So let's say we're inserting 2. What will need to happen?
We'll need to check to see if 2 is greater than or less than 3.
Okay, so if val is less than root dot, I'm actually going to give it an alias because I know I might need to traverse it later on. So kind of similar to traversing the linked lists, I'm just going to say current equals self.root, and then when I want to this current node, that way when I want to traverse it, it's just easier to keep track. Okay, current node equals self.root. I'm going to put this inside the else because it doesn't like where it was before. Okay, so if the value is less than our current node value, so dot value, what will happen?
Self.root.left equals value.
You said self dot what? Root dot,
Root.left.
dot left. Okay. And you're saying that's where I create the new node?
Yes, and you equal that to value, I believe.
Okay. So what happens if there are multiple nodes in there?
So you have to check if there's a value in that node first.
Yeah, so let's say actually here we are creating a new node with the new value. Okay. So there's
Can
another,
we use recursion? Sorry.
what is it? Yeah, recursion,
Can
yeah.
we use recursion right here and actually put 21 inside 14 so we can keep calling upon a new one and just making it a
21.
default?
21 inside,
21, 14, line 14.
okay, 14. Yeah, so you're gonna call insert again to make sure that before you're actually assigning anything to the left, you want to make sure you are in the right area in your tree, because what could happen is you have, let's say 5 here. You have 5, and then below it you have a 3, and then you're trying to go from this 3, you're trying to add something, or let's say you were trying to add a 2 and there's already a 1 over here. Yeah, this would. So you're adding a 2, you see that it's less than 5, so you go left. If you immediately say self.root.left is equal to the new node, then it's going to replace whatever was already here. So the reason why we go back into the insert is we send in, yeah, this is why we wanted to use the root instead of using self. So we would want to send in here the actual root of the node. We can keep self, but
You want to put current node there, default to self dot root?
yeah. So you mean here, right?
Oh, I'm sorry. I was thinking of line 14 where you put root. So if we do a recursion, it just updates there.
Yeah. So self. Trying to think. I don't think I've implemented it with this being inside of a binary search class. Let's just keep it like this. So if we're inserting, that means we need to say tree. No, I don't like that. You guys have any ideas? If we're doing an insert.
Do we need to check on line 23 if it's done first before we do something?
Here?
Yeah, we check to see if the value is good or not. Do we
Yeah,
need to check to make sure the legs are none or not before we
Here we're
move somewhere?
checking- Yeah, we're checking if the value is less than, so we want to move into the left piece.
Oh, so it's checking for none right there.
It's checking for none up here.
That's
Oh.
just in the root on the legs.
Okay. So when we move it into the next iteration, so when we are, I think I can do this. Yeah. So if I do current node dot insert, then we have access to that self. And hold on, now I'm getting confused.
So I'm assuming as soon as you find out which one's bigger, you're gonna want to traverse to the next node. So either left or right. And then when it calls itself again, it's gonna say self.root. And if there's nothing in there, your base case will, I think, stop it.
So you're saying when it calls self.root again, it will.
Because your base case says it's gonna create a new node and put in the new value in there. And then put it as a self node, right?
Yes. How about let's keep insert outside of our class. Let's implement it that way first, and then we can pretty much refactor it and do that. Okay. So inside insert, we're gonna send in the root, and then we're gonna send in the value. And the root is going to be the root of the tree. So when we're calling insert, we're saying like yeah, ignore this part and ignore this part for now. Okay, So we're just gonna start off with nodes and then we're gonna create the structure of the tree. And then we can build a whole class around that. So I'm just gonna delete these. All right. So our tree can start off as a singular node. So we're creating 3. And that is the beginning of our tree. This is the root. I can just call it root actually. Okay. So now we want to update this root. So we can say root equals insert. We send in the root that we have, and then we send in a new value that we want to append. So let's say this is 40. I'm going to insert the 30. So my insert function takes in a root, it takes in a value, it creates, just going to remove these. It pretty much appends what needs to be appended to the list, and then it returns the root back to here. So then we have access to it again. So here when we did this, so if the root was originally null, we say root equals this new node, and then we add this. So that means we don't have to do this. We can just say insert 30, and this should handle sorry, I'm giving it a default of none. Is it this way or this way? Okay. And we want to say 40. And I can print root dot value. Okay. I think this should work. Oh, this one. I am sending in.
Yeah, I think it doesn't need to be equals, right?
What is it?
The none equals none, right?
Yeah, I had it like that, but it was giving me non-default follows default argument. Okay, so I have to also give a default for this one, which defeats the purpose.
I think if you just change the order,
Say insert none and then 30. This is just to start off the tree. Sorry, I didn't. Yeah. Try it again. Okay, now we have this value. If we do this. Okay, so here we're getting none type because we didn't implement this correctly yet. Okay, so inserting to the root of the tree works now. Let's go back to our else statement. So we're taking root as our current node. We actually don't really need to do this anymore. So we're checking if our value is less than our root dot value. If so, root dot left. So we're targeting the left pointer pretty much, and we're going to say it is equal to insert. So we're going to insert a new node pretty much, and we're not going to create the node here. So we're going to call insert again, and then we're going to say we're going to send in the root, and then we're actually going to send in root dot left. And then we're going to send in the value that we want to insert. So what is happening here? We're starting off with a tree that has a singular node. So this node is 30. We're trying to insert 20. So it's going into the left node of the tree. So it starts at root, which is 30 right now. The value is 30. The left pointer is none. The right pointer is none. So because we need to go to the left, we're just going to say root.left equals whatever our insert function is going to return now, because we need to add whatever we want to add to the left. So we go into our insert function. This is the second round. Our root of the tree is now root.left. So now we will end up with an empty root, right? Because we don't have anything there yet. And then it's going to go in here and it's going to add our new value to that space pretty much. And it's going to say that that new node over there is going to be assigned to the original root.left. Does that make sense?
Yeah, I'm only confused by having that first argument with insert being root.left.
This one?
Hey, Zainab, about the does that make sense question, could you just repeat it one more time to make sure I understood?
Yes, yes.
Thank you, I appreciate it.
I wish I can draw this somewhere. I don't have my other laptop out, but pretty much right now, I'm just going to draw it on here. So we have a root. I'm going to just use the Zoom whiteboard. That'll, or not, I don't know how to do this. Okay, annotate, does this work? Okay, so we have a root and we inserted the value 30, right? So this is the value for this root node. Our left is none, and then our right is also none right now. I probably shouldn't have drawn these as circles, but so left and right, there's nothing really there. Oops, draw. Okay, so left and right, there's nothing there right now. So we know that we want to target whatever is on the left side here. So we're going to say that we want to insert into our left side. So sending root.left, that means we are sending in the left node. In our case here, because there's nothing in the place of left node, we're going to get none, which is going to just create a new node. But in the case that there was, so let's say there was already a 20 here. When I'm sending in root.left, I'm sending in 20 as my new root, and I'm sending in the value that I'm inserting. So if I'm inserting 5, then on the second iteration of insert, the root is going to be 20. It's going to be this node here. And then the value is going to be 5. That is my new value that I'm inserting. And then it will once again go into this if statement, checking if the value is less than what I currently have, which is 20, which it will be correct. It will go into line 22. It's going to give me access to my left node pretty much, or the wherever my left node should be, because that's where I know I need to insert it. And if there's nothing there, then I'm going to create a new node and say that this is now my new left side. But if there is something there, then we'll continue the process of checking and stuff like that. Did that make any more sense?
No, that definitely makes more sense. I just think I need to continue like looking at the code version of it, because visually I'm following. It's just how the code is working and how it's constructing this that I start to confuse myself, really.
Yeah, recursion is a little tricky. And honestly, the only way that I can ever understand recursion is by drawing it out and drawing out exactly what is happening step by step. Who else asked for another explanation? Did it make sense?
Don't worry, I was asking about the internal argument, but I think we run it through. We'll see whatever happens. So, it's just with we initially, I think we passed like a none argument. And I don't know if that kind of like throw things off a little bit, but we'll see.
Okay. So yes, right now it's going to be none because there's nothing in my root dot left. So root is, it starts off, root is the top of my tree. And the top of my tree has either a left or a right. And so since my left doesn't have anything, I'm going to insert into my left. I'm going to send this in as my new root, just for computation purposes. And I want to check this value against my new root, pretty much. And this new root is going to be on the left side because we want to insert into the left side. And then else if the value is greater than root dot value, root dot right, would help if I can spell this. Okay, insert. We're gonna do the same thing, so we're gonna just call root dot right and then send in the new value that we're doing. So in the case that they're equal, we don't really want to do anything. We're just going to return our root. Because since this is a binary search tree, things need to be in order. And if something already exists in there, we don't really need it. Okay, so after all of this, I just need a return statement here to make sure that I'm returning whatever needs to be returned to the above one. And then, yes, this should work. So when I insert 30, I know if I insert 20, it's going to go into the left one. So I can say root dot left dot value. And this should give me 20. And it does. So can someone explain what is happening line by line now, since we've seen that it works?
I'll take a crack at it. Which line did you want me to start at?
Start with so what happens with the first insert, what happens with the second,
Mhm.
and then I'll
Okay.
add a third one. One sec. Insert, we're gonna send in our root, and we're gonna send in 21.
Okay, so line 37, when you insert none and 30, so root equals none, so it'll trip that first if statement and set the value of the node at 30, and that is like our master root, if you will.
Mhm.
Then we insert the previous root and 20, and since the root exists, it's no longer none, so we'll trip the else statement, and then we go down to line 23. The value of 20 is less than the value of 30, so root dot left, we insert the next node.
Mhm.
And then when we hit 21, we do the same thing. That one goes left of the original node, but we're not done. So it goes through again and then trips the aleph and puts it to the right of 20.
Okay. So on that, so can you mention, let's go back one more. Actually, yeah, thank you. That was correct. So that will go on the right of 20. Can someone else explain it one more time and mention what is being sent into insert here? Like, what is the value of this node every time it's
That's non-initial.
It'll be a none, right?
so on the first one, it's actually first one doesn't go in here. On this one, on insert 20, root.left is going to be none because we only have one node, and that node, like we saw here, the right and left are going to be none when it's defined. So now our tree looks like we have one node up here and one node down here to the left. So when we're inserting 21, first iteration, we send in the root of our tree, which the root starts up at the 30 node. We know that 21 is less than 30, so we have to go into the left. So this gets called. So root.left here is going to be our 20 node, the one that we just inserted, as well as 21, which is our new value that we're inserting. And then, so when this gets called, insert the root at the top here is going to be 20, or the value of this root is going to be 20, value is 21, goes down to here. It calls insert with root.right, and that 20 node is has still none for both the left and right. So this is going to be none, this is going to be 21, and it's going to create a new node 21, and then it's going to return it. So when it returns that new node gets assigned to the 20.right. So the node that had the value 20.right, that's what it gets assigned to. And then, so this is done, right? We have now the 20 node with the 21 node to its right. And then we come down to this return statement, it returns. So this call was called from a previous root.left. So that means it's going to take that 20 node and that 21 node that was on its right, and it will say that this is part of the original root.left. Did that make sense? Should I draw it again?
No,
Yeah.
I mean, it makes sense. I think, okay, no, go ahead.
If you could draw it again, I'd appreciate that.
Yeah, definitely. Okay, so first insert, we're putting node 30. Okay. Second insert, let's change the color. So second insert is, we're inserting 20. So first iteration, we go in our root. Actually, I need a better way to draw these. Okay, it's fine. Okay, so it goes here, our root equals 30. So this is root. Root is 30, val is 20. Okay, 20 is value over here. This is what we're inserting. We go in here, we say that the root is not none because there's already a node in here. So we go in under here. We check if the value is less than the root value, which it is. So that means that we're gonna say, okay, let's make another function call, but whenever that returns, we're gonna set it equal to root.left. So root.left is going to equal whatever this function call returns here. Good so far? Okay. So we go into this function call. This time, root, we're sending in the original root.left. So we're sending in this now. And right now there's nothing there. So that means it's going to be null. So It's not that anymore. It's going to be null. We get here, or none. We get to this point where we look at the root, we're like, okay, the root is none. So we need to create a new node with the value 20. And we are going to return it. So when it returns, it ends up back here and it gets appended over here. Okay, so that is the 20 insert. Everything good with that? Good, good, okay. Let's do our third call. Let's do an eraser. Okay. So our third call, we're trying to insert 21. 21, okay. So we start off with the root pointing to 30, right? Because that is what, oh, I can't scroll down anymore, but that is what we sent into the original insert down here. So it takes that, it looks at, it compares the values. It says, okay, we need to go to left. Then it's going to do the same thing. It's going to say whatever is on, whatever this function call returns is going to be assigned to my left node, or to my left pointer, pretty much. So now we have a new function call, or in a new insert, where our value is still 21, but our root is now pointing to 20. So it's not that one anymore. Okay, so now our root is 20. It's not none, so we're not gonna go in here. We're gonna go into the else. Is 21 less than 20? It is not. Is 21 greater than 20? It is. In that case, let's say we're gonna insert something on the right side. So whatever this right side equals, or whatever this next function call returns, we're gonna put onto our right side. So we call insert again with root.right, which, so for our third call, it's going to be none. And we're sending in 21 again. So back up here, because it got called again, sorry, this got called again. Root is equal to none, value is 21. Root, yeah, so we create a new node with the value of 21, and then we return it. So when it returns, it goes into right here, root.right, and our new node got appended to the right side of 20. And now, since we're done with that, this returns, it gets down to this return point. And if you guys remember that this iteration was, it was pointing to here, this was the root. So it's returning 20 with 21 appended. And when it returns actually into this function, right? Because it said in the beginning it was root.left, and then we called the insert. So it goes back up to where the root was 30, and it's saying root.left is going to equal what was returned, which that function had returned a node with 20 with a node 21 to its right. Does that?
Yeah, that seems to make more sense, and maybe I'm getting ahead of myself right here, but assume the third number that went in was 25.
Mhm.
So 25 would also be placed on the right side of 20.
Mhm.
Then what if the next number called in was 21, and which would be on the left side of 25, correct?
So, oh, so you mean instead of 21, if
Yeah,
it was 25, yeah. So
25,
let's say
yeah.
here, yeah, if here was 25, it would have to insert 21 on the left of that.
Left side, okay. And
Yeah.
now, does that current code on line 26 and 27, does that account for that? Or, because that's what I'm not understanding, is like, what if the value was greater than the left value, but less than the right value. I guess what
Yeah,
I'm not seeing is like,
So it pretty much starts at a node by node basis. So it pretty much just checks whatever you're trying to insert, is it greater than or larger than the current node that you're at? And then if it's less than, then it will say, okay, let's go to the left and let's explore the node that's there. If there's no node there, then we insert the node right there. But if there is a node there, then we grab it. So let's say we went to the right side, right? We wanted to insert 21 after 25. It went to the right side and said, okay, let's evaluate what's on the right side of 20, which is 25. And then it says, if it's less than, go left. And then there was nothing there. And so we inserted the 21 right there. So pretty much what it's checking, the moment it goes to a node, does this node exist? If it doesn't exist, then we can just create a node here and that is done. But if there is a node there, we want to see, okay, I can't take this spot, so I need to go either left or right. And I need to check if I should go left or right based on the value that I'm trying to insert. If it's less than, go left, more than, go right.
okay, so after each node, it basically, everything basically starts over to compare with the next number, correct?
Yes.
So like, okay, that makes sense then, because yeah, I didn't think the whole thing started over, so I was kind of wondering, how we're still iterating through, comparing it with the left and the right values. But yeah, if it starts over after every node it goes, that makes sense.
Yeah. And the way it starts over is by us sending root.left or root.right. That is kind of how it starts. Instead of starting at the top of the tree, it starts at whatever node we got to. Yeah. Other questions?
The question. So why does it keep restarting the root at the top 30 if down at 37 and 39 it looks like you're setting the root to 20 there, like it's being replaced?
So, one sec, I can't keep this. So here, we're replacing it by the entire tree coming back. So each run of insert, whether or not we okay, let me see. So when we had 2 nodes and we were inserting a third one, we had to do 3 insert calls, right? So there's one, and then within that one, there's another one, and then another one that happened after that, right? So when this third one returns, it will return to the second one. When the second one returns, it'll return to the third. And that last one was the original one that was called. And this will always return the entire tree from the start, because we were starting it off with the initial root. So it will return a tree with this node inserted onto it, with 30 onto it. So when we say here root equals insert 20, the reason why it's not overriding it is because we're sending in the original tree. So we send in the original tree and we're gonna say, okay, take this original tree, traverse it and figure out exactly where to insert, and then insert that and return the new and improved tree, the updated one. So here we're not actually like this root and this root at the top, they're the same. Both this one and this one start at 30.
Okay, so I guess I'm just getting a little confused because it's called, so if 41 was named like second number, and then in 44 instead of root it would have to say second number and 21.
Yeah. So root was sent in, or root was our initial tree, we created root 2 out of our initial tree plus 20. And then when we wanted to create our last one, we just sent that in because that was the most recent version of that, pretty much.
Okay, gotcha. It's just like the connecting thing, like the linked lists, how each node was connected
Yeah,
to each other.
Exactly.
I get it now.
yeah. Okay. Let me show you guys a neat function that we can write real quick. So with trees, there are 3 different ways of traversing them, and this is all with recursion. So there is in order traversal. Did I write it in order? Yeah. And then, so traversal just means going through the entire tree, like one node at a time. So there's in order, there's pre-order traversal, and there's post-order traversal. And pretty much what this, let's actually just do the in order one. So if we have a root, if there are any nodes to print, we are going to print root.value, but not before we actually traverse all the way to the left. So we're gonna call, oops, root.value. So we're gonna call this function again with, sorry, not value, with the left side of the tree. And then afterwards, we're gonna call it with the right side. In order, right. I would recommend you guys play around with this because it's gonna probably take a little longer to explain than we have, but in order. Okay, so I send in a root of a tree that I have, and then let's see how it prints it out. In order, I didn't send anything in, did I? Okay. There we go. What am I doing wrong? Value. Root.val. Value. Okay, so in order traversal allows you to print out an entire tree in a certain order. So here we go. Hold on, sorry guys. We go left, we go right. I'm gonna copy these over just so we can see the difference in between them. So pre-order, and we have to print. Actually, I'm gonna copy those. And post order is the opposite of this. So I'm just gonna do. Just gonna insert a few more So our tree looked like 30 and then 20 and then 21. I'm gonna also say, I'm gonna insert in a 19. So there's one on the left as well. Okay, so what this tree is gonna look like is 30, 20, 19, and then 21 here and here. So 19, 20, 30. Okay. So if I run this, I'm going to print in order. Okay. So let's, did I do the print? Yep. I think that was the only one. Oh, I didn't say if root. Sorry about that. Okay. So basically we're checking if there are nodes, let's print. And these are just 3 different orders to print in, and we'll see the differences between them. Okay. So what in order does, it will print everything from smallest to largest. So it prints 19, then 20, then 21, then 30. Pre-order prints everything from the top of the tree as you're traversing it. So it goes to the first node, it goes then to the left, then it goes to the left of that, and then it goes to the right of that. So if we added, let me add some more nodes on the right. So I can say root, I'm gonna insert root and then 40, and then I'll do the same 41, and then I'll do the same with 39. Okay, so what our tree now looks like is, since I added those, just gonna do, I have, so 39, I added here, 39, and then 40, and then a 41 over here. So in order, so if you write your print function like this, where you call this function again for the left tree and then print and then call it again for the right tree, it will print everything in order. Why is that? So let's start at the root, right? We're starting at 30 here. It calls this function with the left subtree. So now our new function is at 20. It's gonna go to this line again, and then it's gonna give you the left subtree, which is 19. It gets here, there's no, sorry. So root is none at that point. like the left subtree is none. So we return, it comes back to where the root was 19. So this has returned. Now we execute this line, it prints the value, and then it goes to in order right. So it goes to that right side. There's nothing there, so it just returns. So now we're back up to 20. So 20, this part has executed because it already explored the left side of that tree and it printed them out. So, so it explored the left side. We don't have to worry about this one. It goes on to the next line. It will print out 20, and then it's going to explore the right side of 20. And then when we're in the right side of 20, it's going to print out whatever's here. I think here was 21. Yeah. So it prints 21. So it just keeps going recursively like that. Pre-order traversal is going to print first and then traverse. So with the pre-order, we printed 30 and then it went to 20. And then, so because we printed and then we went to the left side, right? And then it prints. Then we go to the left side again, and then it prints, which is 19. After we go back from coming to the left side here, we go to the right side, which will print 21. So after 19 was 21, right? And then we go back, okay, 20 has already printed, 30 has already printed. That means we have to go to the right side of the 30 node, which is 39. I know this is a little confusing with the traversal, but if you ever need to print out a tree, this is the way to do it. And then post order, you pretty much traverse first and then print. So you're printing out the children first, and then you're printing out the parent versus, yeah. I don't know. I'm not gonna go too much in detail into these, but just to kind of understand that there are 3 ways of printing out your trees. And yeah, if I actually swapped, if I swap the right and the left here for the post order traversal, we get a reverse list. No, we don't. Never mind. It does start back here. So it starts 40, 41, 40, 39, and then it prints out 21, 19, 20, and then it prints out 30 at the end. So it explores like the right subtree and then the left subtree, and then it kind of goes back up. I know this was a lot. How are you guys feeling? Good, shaky? Helpful? Okay. Glad. Yeah, this does take some practice, especially with using like recursive functions to kind of iterate through trees. Yeah, it takes some getting used to for sure.